The example we're going to work on first, hopefully we have time to do two, I'm not sure, is going to be to look at an initial value problem given by y prime plus 3y equal to 13 sine 2t with initial condition y of 0 equal to 6. So this is a first order linear problem. You knew how to solve these during exam 1. But we're going to use this new method we learned, Laplace transforms, to solve it. And it'll be probably harder than the method we learned during exam 1, but this method can be applied to more complicated problems as well, which is why we cover it. So we're just going to follow these steps right here that I lined out for how we solve initial value problems using Laplace transform. And that first step was to take the Laplace transform of both sides. So we're going to want to take L of y prime plus 3y. And we're going to want to take L of 13 sine 2t. And I gave myself a little space to do that first Laplace transform. We might move that 13 sine 2t depending on how it goes. So when we're looking at this first Laplace transform, L of y prime plus 3y, we're going to remember the different properties that we can use. And the first one is linearity. So that's going to be the same as L of y prime plus 3 times L of y by linearity. And then from here, we've got two different Laplace transforms that we have to take. And so the second one right here, L of y, is pretty straightforward. We always say that the Laplace transform of little y is capital Y, a function of s. And then the Laplace transform of y prime, we have to use our derivative property. So this is a first derivative. So we're going to start with s to the first power right there. And then we're going to subtract something times 1. And then the way we fill in that is always that the highest power s is multiplied by y. And then we start filling in our initial conditions until we run out. In this case, there's only one space and one initial condition, so that's what happens. I'll go ahead and say that that's our derivative property. And then since I left that space right there, we'll go ahead and also start to kind of simplify this. So that's s plus 3 times y. All I've done is combine these two terms that were multiplied by y, minus y of 0. And we could take that one step further. We always should. We can plug in what y of 0 was. It's minus 6 from right up here. And we'll call both those steps algebra. And this is going to be something that's important to us later. As far as L of 13 sine 2t, we're going to have to look at our table of Laplace transform, so hopefully that's somewhere convenient for you. But the thing that's going to be important for us is that L of sine kt is equal to k over s squared plus k squared. And so if we're looking at L of 13 sine 2t, we know that that's 13 L of sine 2t, again by linearity. And then that 2 means that k is equal to 2. So L of sine 2t is just going to be 2 over s squared plus 4. All right, s squared plus 2 squared. So that's, when simplified, just, I'll do it in the next line because this one is L of sine. And then when simplified, that's just going to be 26 over s squared plus 4. And that right there is also going to be important to us later. So far we've done step 1, take Laplace of both sides. And we'll continue on this page. Our next step is going to be to set both sides equal. So that's going to be that s plus 3 times y minus 6 equal to 26 over s squared plus 4, I think. S plus 3y minus 6, 26 over s squared plus 4. Yeah. Okay, real quick, I'm going to take you back to when we wrote those steps down, though. And remember, I made a point of saying when we set both sides equal, there should be no yt left, and we should have an algebraic equation with no derivatives. And so I'm just going to bring attention to where that happened for us. So we started with t's right here in our 13 sine 2t, but when we took L of 13 sine 2t, everything turned into s's instead. That was a t before. And then we used to have little y's on the left side of the equation, but those either became capital Y or a combination of capital Y initial conditions and s's. And so when we look at this equation right here, we've got s's and we've got capital Y's, but there are no t's or little y's, and all of our derivatives are gone as well. And I know that it seems like that's kind of a silly thing to point out right here, but as these problems get more complicated, it's going to be even easier to miss just like one term. So always check to make sure that you got all the terms and there are no little y's or t's left, because if there are, you can't solve the rest of the problem. So I'm just going to put a little check mark there that says that, yep, we see there are no y's, t's, or derivatives. And from here, what we have to do is solve an algebraic equation for y. Capital Y, that is. And so we've got s plus 3 times y would be equal to 6 plus 26 over s squared plus 4. And we've got dividing through by s plus 3, y would be equal to 6 over s plus 3 plus 26 over s plus 3 times s squared plus 4. And then at this point, I've actually done step 3. So remember I said in step 3 you'll solve for y of s equal to some stuff, and I said but it'll be different every time what that stuff is. That stuff for us is this sum of two fractions right here. That's what big Y is equal to. And so now we're on our last step, which is where a bit of trouble can come up. Because thinking ahead, what we're going to be doing is take the inverse Laplace transform of both sides. So I'm going to go ahead and write out what that's going to look like. We're going to have L inverse of capital Y is equal to L inverse of 6 over s plus 3 plus 26 over s plus 3 times s squared plus 4. And so on the left side, that's just going to give me y of t. And then if I can take this inverse Laplace transform right there, I'll be done. I'll have little y of t. But that inverse Laplace transform is going to take us a little while to solve. The reason being because right here we have a term where we've never learned how to take an inverse Laplace transform of something like that. And what we're going to have to do is partial fraction decomposition so that it looks like something we can take the Laplace transform of. Unfortunately, I cannot do that in like under a minute. So I'm going to go ahead and stop here and we'll pick up the example in the next video.